When asked about the difference between acids or bases or what makes an acid, most people initially start out with talking about pH. And of course, pH is a major factor of what makes an acid an acid. And most of you already know that for acid solutions, the pH is going to be less than 7. Technically, you're going to find out that the pH range goes from generally from 0 to 14, but it can go beyond 14 and less than 0 as well. One of the other major points with acids and bases, or in this case acids, is that the major ion that makes an acid is called the hydronium ion. There are a couple different ways of writing the hydronium ion. I like to write it as H+, which is the shortest, easiest way. Essentially, it's just a nucleus of a hydrogen atom. Another way of writing the hydronium ion, which you'll see in your book, is written as H3O+. In both cases, it's a positively charged ion. It's present in all acid solutions. The only difference between these two is that one is written in the presence of water, and the other one, it's assumed that water is there. In other words, what you're doing is you're just taking really a water molecule and you're sticking on another hydrogen to make it H3O. If you remember the electron dot diagram for a water molecule, it has obviously oxygen, it's bonded to 2 hydrogen, and it has 2 unbonded electrons. These unbonded electrons are what attract the other hydrogen to make up the difference between H2O and H3O. It doesn't really matter whether you write the hydronium ion as H+ or H3O. In both cases, it signifies the fact that if there are a lot of them, then that is an acidic solution. If there's not very many, then it's not as acidic. There are hundreds of different acids, and you already know about 6 or 7 of them. There are 6 strong acids. Here are the 6 strong acids. Hydrogen with iodine, hydroiodic, and then you have hydrochloric, hydrobromic, nitric acid, sulfuric acid, H2SO4, and perchloric acid. The 6 strong acids represent acids that you're going to find out that make a lot of hydrogen when they go into water. Weak acids do not make nearly as much H+ or nearly as much hydronium. There are many, many, many more weak acids. I just wrote down an example of 3. Vinegar, otherwise known as acetic acid, which has the formula of HC2H3O2. There's lactic acid, there's nitrous acid, and there are lots more. There's a big table actually at the end of your book that lists some of the weak acids out. Again, the one common feature that all weak acids will have with strong acids is they'll all have hydrogen at the very, very beginning. That is to denote the fact that it isn't an acid, and it also denotes how these acids react. A lot of people think that acids are caustic, and that is generally true. Some acids can be caustic or burn, but bases are equally as caustic. As a matter of fact, bases sometimes actually do more damage. And not all acids are caustic. It more depends on the concentration of the acid than it does the fact that it's an acid. Some of you have heard of litmus paper before. It's an indicator. In the case of acids, it changes blue litmus paper to red. The last thing that most people remember about acids is that if you were going to taste an acid, which is not generally a good idea for chemistry lab, acids generally taste sour. The classic example, of course, is a lemon, and lemons have citric acid in them, which makes it very, very, very sour. Now, generally speaking, bases are the exact opposite of acids. They typically have much higher pHs, that is, the pH of most basic solutions will be greater than 7, and most bases run from 7 to 14. The other thing about bases, unlike acids, is they have a different ion, which indicates that the common ion for all bases is called the hydroxide ion. And obviously, it's a nice little feature that if you take a hydronium ion, which is H+, and you take a hydroxide ion from a base, which is OH-, they will react together to make H2O. That's why acids and bases neutralize each other. But that's for another day. When you look at strong bases versus weak bases, there are a number of strong bases that you already know. If you can remember the solubilities rules that involve the hydroxide ion, the hydroxides are generally insoluble, but there are a few that are completely soluble, meaning they make a lot of ions. Those are the alkali metal hydroxides like lithium, sodium, potassium, and so on from group 1. Those are examples of strong bases because they make so many ions. In addition to the group 1 ion alkali metals being soluble, strontium hydroxide and barium hydroxide are 2 additional strong bases. There are, again, many more examples of weak bases. The most common one that you're going to see in your book, and you probably already know about, is ammonia. Ammonia has the chemical form of NH3, and when ammonia goes into water, it makes lots of hydroxide ions. One of the other things about bases is if you tasted a base, not all bases do this, but it's not a good idea for a chemistry laboratory. In a chemistry laboratory to taste bases, but bases generally are associated with a bitter taste. If you think about really strong coffee, that is bitter. And the last thing about bases is that bases turn red litmus paper blue, and it's a good way to tell this if something's an acid or a base.